Ladies and gentlemen, I'm pleased to welcome you to this Memorial Year Alan Cox Memorial Lecture and to introduce this year's speaker, Rob Coe. Rob was born in Toronto, Canada. He graduated Phi Beta Kappa in chemistry and physics at Harvard before moving to the West Coast, where he obtained his master's and his doctorate degrees in geophysics from the University of California at Berkeley. After a couple of years of postdoctoral stay at the Australian National University, in 1968, Rob joined the staff of the University of California at Santa Cruz. He has spent the bulk of his professional career there, where he has been full professor since 1978. In that time, he has also held visiting professorships during sabbatical terms in Paris, Beijing, Hawaii, Lanzhou, and Montpellier. He's widely traveled. Rob was elected a Fellow of AGU in 1988, and he has served the Geomagnetism and Paleomagnetism section as President-elect from 1994 to 96, and then as President from 1996 to 1998. Rob has numerous publications to his credit, covering a wide range of topics. In particular, he's made major contributions to determining geomagnetic paleointensity. He's also made extensive paleomagnetic studies relating to the paleogeography and tectonic evolution of North and South China, and he's used paleomagnetism to try and work out the complex tectonic history of volcanic terrains in Alaska. His papers include rock magnetic studies in sediments, the application of magnetostratigraphy for dating sediments, and the use of magnetic anisotropy to determine the directions of magma flow during flood volcanism. Rob is especially interested in long-term geomagnetic field behavior, including reversals, excursions, and also polarity transitions, and in trying to understand how these phenomena shed light on the origin of the geomagnetic field itself. So Rob has himself made many valuable contributions in many of the research fields that absorbed Alan Cox, after whom this lecture is named. It's my great pleasure now to invite Rob to deliver the Alan Cox lecture for this year on the subject of understanding geomagnetic reversals.
Thank you very much, Bill, and thank you everybody for coming. I'll give you a little outline of what I'll be talking about. Understanding geomagnetic reversals. It's going to be, and I'm going to move up here soon, so you'll be able to hear better. I'm going to be showing you a combination of paleomagnetic observations and geodynamo simulations. As you know, paleomagnetic observations are fragmentary, to put it mildly, and the coverage in space and time is very, very sparse. We're not able to get a spherical harmonic representation of the Earth's field, even in a fairly crude way, back more than 3,000 years ago. And I don't know if we'll ever be able to do it a million years ago, over the past million years, although it's very dangerous for an old guy like me to stand up and say, oh, we're not going to be able to do this or that. But anyway, we're a long way away from that. On the other hand, geodynamo simulations give us simulated data wherever we want it with very high spatiotemporal resolution. And I'm going to go over there. And not only on the surface of the Earth, but down inside the Earth. So the trick is to connect the two in some way that improves our understanding of the real magnetic field. That's the goal. And I hope I'm going to be able to convince you that already marrying the two has produced some significant insights, some of them new, and that by using these advances to guide further paleomagnetic sampling and refining the geodynamo models that produce the simulations, that there are more important results to come. The outline of the talk is simple. I'm going to tell you some things about what happens during reversals and excursions as far as we know from observations. We're going to get into the question of how reversals are triggered, or even whether that's a good word for it is debatable. We're going to look at the question of very short and very long polarity periods, cryptochrons and superchrons, and then I'll close by some thoughts and some results about symmetry, stability, and even some speculations about the early geodynamo. Now this, what I'm going to be talking about, they're the fruits of the labors of many, many people, including a lot of you right here. And I'd like to acknowledge that right from the beginning, and also to give some special thanks to students and very close collaborators. For instance, students Joe Liddicoat, Scott Bogue, Jonathan Glenn, USGS collaborators Ed Mankinen and Sherman Grome, French collaborators Michel Prévost, Pierre Camps, Lionel Ongre, and of course Gary Glatzmeyer and Paul Roberts, without whom half of this talk, the simulations part, wouldn't be possible at all. Well, this is the Alan Cox lecture, and I was fortunate enough to be a field assistant in 1964 for a sampling trip to Nunivak Island, which Alan led. And here you see us in our boat with two USGS geological colleagues and our Eskimo guide, Henry Shavings. This is when Alan and Dick Dole and Brent Dalrymple were in the middle of working on the last several million years of the polarity timescale. And together with other groups, especially Ian McDougall's group from ANU, this now familiar polarity timescale was established by studies just like this. It had a huge effect on me, this trip. I was working on thermodynamics of phase transitions at the time, or that's what I thought I was going to do my thesis on. And I got so, Alan is really a consummate teacher. I never had him in a class. He was at the USGS, I was at Berkeley. But he really got me hooked on how does the Earth's magnetic field behave, and what can it tell us about the interior of the Earth. I think in this paper, this 1968 JGR paper, to my mind is Alan's most creative paper of all the creative work that he did. In this paper, he was thinking about the length of geomagnetic polarity intervals. He combined inspirations from a very crude model, the double disk dynamo model of Rikitake for geodynamo, ideas, qualitative ideas about perhaps much of the dipole field has a deep origin, and non-dipole field, shallow origin in the core of the Earth, and combine that to this into this diagram, in which what is pictured here is schematic idea of what the axial dipole intensity might have done as a function of time, swinging high and low in intensity, and sometimes reversing. And here is shown even more schematic idea of the random or statistical behavior of the non-dipole field, or actually the non-axial, the total field minus the axial dipole field, which I'll call a non-axial dipole field. I think Ken's designation of the SAD, the sans axial dipole field, is probably better because it's not as ambiguous. But anyway, that's what is meant here. And what you see is his basic idea, which was that if the non-axial dipole field sources happen at some particular time to add up with the opposite sign and equal intensity but opposite sign of the axial dipole field, then you might trigger a reversal. So here is his idea of where a reversal might have been triggered by this non-axial dipole effect. So it's, in that case, the frequency of reversals, the probability of a reversal would depend on the intensity of the axial dipole and the statistical nature, the statistical fluctuations of the non-axial dipole field. Now, we don't have any way paleomagnetically to get this non-axial dipole field signal. In fact, it's just schematic here. So obviously, this is a place where the simulations will help us, may help us. This one I don't need yet. In 1969, he followed up with a paper in Science in which he showed that the simplest interpretation of this model, when thinking about the lengths of polarity intervals, will yield a Poisson distribution for the distribution of polarity lengths. And he showed that with the data then available, that fit reasonably well, except in the very short time intervals, less than 100,000 years, not shown on that diagram. Well, of course, the geomagnetic polarity timescale right around then, and much work since then, has been extended far back in time, and we have a relatively good record back 160 million years ago, if you can read it, as shown in papers here by Kent and Gradstein and Candy and Kent. As well, we know that there are some very short excursions, I will call them, to have a non-genetic description of them, excursions of the magnetic field during the last polarity interval. And of course, they're being found back farther in time now. But here they're shown, the Lechamp event, the Blake event, some others that we've heard about in talks given just this year at AGU. And in particular, I'll mention some about the Blake event later. So what happens during reversals and excursions as far as we know? Well, how long do they take to happen? Very early estimates have held up pretty well. You can just look at the fraction of lava flows that you sample with random sampling of lava flows, count up the number that have intermediate directions of magnetization between normal and reversed polarity, and come up with an estimate. And Cox and Dalrymple did this in '67 and came up with 4,600 years, but with a very wide confidence interval. Or more directly, you can look at sedimentary records as a function of stratigraphic position, and knowing the sedimentation rate or having an estimate of it, you can look at the variation in direction or intensity, say the low intensity during the transitional part of the reversal. And Opdyke et al. Also came up with about 5,000 years. Probably there are large variations, perhaps at least between 1,000 and 10,000 years for different reversals, and maybe even more for some oddball ones. Well, then to give you a flavor for the data, I'd like to show you results from two of my favorite studies. One of them is a record of a reversal recorded in lava flows at Steens Mountain. Here you see a bunch of superposed lava flows that luckily were erupted during the reversal. Or also I'll show you results for the Mono Lake excursion recorded in the sediments of Mono Lake, California. Beautifully flat-lying sediments, some of the best sedimentary recorders I've ever seen, with ashes that can be correlated all around the lake. So on the left here, you can see the variation of reversal angle and paleotensity as a function of thickness from the top or stratigraphic position in the lava flows. And over on the left here are full polarity directions. You can see the reversal angles swing off to transitional directions here, pop back to well, in this case to normal directions, and then proceed to transitional and finally back to stable normal directions. And the field intensity, which is on a log scale, drops during the transition. It recovers its almost full polarity value as the field recovered a normal direction in the middle of the transition, then dropped low again and recovered actually a high value after the transition and swung back and forth before it settled down. I hope that you can see that better than I, because I'm so far away. But anyway, here, all you need to see is that from several locations around Mono Lake, there are records of an excursion which look very, very similar from one locality to the other. This happened about 30,000 years ago, 30,000 years ago. This reversal was about 16 million years ago. And the directions did not achieve anything like fully reversed polarity in this Mono Lake excursion, as recorded at Mono Lake. Well, in paleomagnetism, we like to express these in terms of VGPs, virtual geomagnetic poles. So the same record, directional record, translated into these poles for Steens Mountain starts out reversed, goes to transitional directions corresponding to VGPs around western South America here, jump up to normal, then come back to transitional, and during this time the intensity went up and then went down again, and then completes the reversal on kind of the backside of the globe over here. Whereas you can see in the Mono Lake excursion, none of the VGPs get anywhere near the reversed polarity. And that's why we call it an excursion, not necessarily an aborted reversal, although then you get into really semantics. Well, looking at this information-packed diagram about the Glatzmeyer and Roberts geodynamo simulations on the left here first, I won't spend really any time talking about all of the physics that went into these simulations, which you can read in a number of really good papers that have been published by Glatzmeyer and Roberts on this. Suffice it to say that these are the only simulations so far that I know of that are as physically realistic as they are, that also produce reversals. So they're the simulation of choice right now for studying reversals. And what is it that drives the geodynamo anyway? Well, I think we all agree that it's controlled by the amount of heat that can get out of the core. Because if no heat could get out of the core, then convection would stop and crystallization of the inner core would stop, and those are the main sources that we can think of to drive the geodynamo, unless perhaps precession could do it by itself, which I don't believe anyone thinks. So what you see here are various imposed heat fluxes at the core mantle boundary in these simulations. And we're going to look at examples from only a few of them. We're going to look at model G, in which the heat flux is uniform over the core mantle boundary. And we're going to look at model H, the so-called tomographic model, in which the heat flux varies above and below the average, above in red, below in blue, scaled to lower mantle tomographic velocities. We're also going to look at model C, which has low heat flux at the poles and high CMB heat flux in the equatorial region. And we're going to look at model E, which has also high heat flux at the poles, but at the low heat fluxes at intermediate latitudes. And what you can see right off, looking at the true dipole pole latitudes, is that model E had no reversals in 300,000 simulated years. Model C had many reversals and excursions. Model G, the homogeneous, had 2 reversals in that length of time, otherwise quite quiet. And model H is very noisy, and it had 2 reversals. So we'll come back to talk about these. Over here, we see the spatial spectra at the Earth's surface, where what's plotted down here is the Rn defined up here. And these are G and H are the Gauss coefficients, and we'll call this loosely the energy spatial spectrum. Energy. It's actually the energy density in terms of units of the field at the surface or at the core mantle boundary in some cases. So the Earth's values from MagSat data, soon to be supplemented, well, more than supplemented, soon to be completely redone by new satellite results, are shown here. And the 2 models, homogeneous and tomographic, G and H, are shown here. And you can see they have very similar form. All 3 are dipole dominated. The intensity of the simulations is weaker than that of the true Earth's field. And there are a variety of reasons for this, one of which is the relatively low resolution that these simulations are run at. Higher resolution simulations produce larger fields, but they can't be run long enough to get reversals because time step has to be too small. Perhaps more important than any of that is I'll be talking about the axial dipole and non-axial dipole energies in various topics to come. And by that, I mean for the n equals 1 and m equals 0 term here involving G10 and H10 squared, that's the axial dipole energy. And then the total summed over, well, up to 21 Gauss coefficients, which is the resolution that was saved for these runs. The total energy minus the axial dipole energy is the non-axial dipole energy. Okay, in the homogeneous simulation, let's see how we're doing here. In a homogeneous simulation, here indeed is plotted this energy, the non-axial dipole energy in red, the axial dipole energy in blue, log scale here, time, simulated time, plotted down here. And then the graph below, which is busier than you'll have time to take in, is an example of the, as seen from one site, in this case 40 degrees north, 240 east, has one can see the course of the reversal in terms of reversal angle direction going from one polarity to the other with a bunch of swings in the transition zone, and axial dipole and total field intensity at this site, how it varied through the transition. But the thing to notice really is up here on the top diagram that there is what considerably less average non-axial dipole energy than that of the axial dipole, and then there are two places where the axial dipole energy plunges. In the first case, we don't see any suggestive swing of the non-axial dipole field that might have triggered this instability and this reversal that happened here. In the second case, there is such a thing that you might be able to see right there that we could call a triggering of that reversal. And you can see its effect in terms of the total field intensity right here. In terms of the VGPs, well, not just the VGPs, another advantage of the simulations is we can know what the true dipole did during that second reversal here. And this is what it did. And just to remind us that even for this case, the non-axial dipole field has a big effect on what one would see paleomagnetically at this given site, for instance. We see a rapid reversal, but then during this second phase of what the true dipole was doing, there's a huge, mainly non-dipolar trip around the globe of the VGP and several other smaller loops down here. If we look at the tomographic simulation, similar diagram, you can see first of all that the non-axial dipole energy is much closer to the distance between it and the blue axial dipole energy is less. And indeed, each of these little spikes here, again with a log scale, so even this spike, a very large excursion of the field here, another excursion of the field here, a quick clean reversal here shown below, a couple more excursions here, and a long messy reversal happened here. So tomographic simulation with the same total CMB heat flux, but with a longitudinal and latitudinal variation is much more prone to reverse, has much more unstable polarity times than the homogeneous result. You can sort of stare at this for a while and see what happened at this site here. This is Iceland, through the reversal. But I just wanted to draw your attention to, in this case, you see the non-dipole field energy, non-axial dipole field energy going up very significantly as we approach this reversal. And this was just before the directions started to go off. This is the vertical field at the surface of the Earth, just before the field started to reverse, strongly dipolar, as you can see. And only 400 years later, the radial field has produced foci of 40,000 and 36,000 nanoteslas, like 2.5 times greater than what the field was here just 400 years before. And whether you want to call this a trigger of the reversal, it's a little late to be a trigger. It's what happened around the beginning part of the reversal. I guess, again, that's semantics. So the take-home message here is that reversals vary a lot in their character in these simulations, and I don't see any reason to doubt that they vary a lot in terms of their detailed signatures, their durations, how the intensity couples with the directional changes in nature either. Looking at the VGPs, or the true dipole path, and the VGP path for this location, you can see, interestingly, the true dipole path goes over the Americas, and whereas the VGP path for this site, again affected by the non-dipole field, it actually crosses over Africa, so considerable distance away, although this rebound here, much like in the Steens record, you remember the rebound in direction, is associated with this move over the Americas. So here, this one VGP record correlates in position of the VGPs with the true dipole, whereas for the main phase of the reversal, it doesn't. Well, this gets us into the question of preferred VGP paths, a topic of considerable interest for those of us who like to try to relate geomagnetic field behavior to properties of the deep mantle. Brad Clement pointed out in 1991 that the last reversal had, if you looked at all the records that were available then that passed muster, one found VGPs that lay in two longitudinal bands, of which, one correlating with the Americas and one correlating with East Asia, Western Australia. And Ken Hoffman, in a paper published in 2000, has brought this up to date, and the colors you see here are the VGP intensities for more reversal records than Brad had to work with. And indeed, you still see this same sort of preference, although you also see some high VGPs over here in Africa too. So here we have one reversal whose true dipole path goes over the Americas. So we wondered whether to make anything out of this from our simulations where we don't have many reversals to look at, as Carlo Lage had to compile also back in 1991. Here we have multiple records of reversals, and their VGPs again are seen to cluster over in preferred bands over the Americas, over this region in East Asia, a secondary pile over here in Africa. And one of the things that was pointed out in this article was the striking correlation with the lower mantle tomography, seismic velocities. This result was then intensely debated, and I'm sure we would still not have unanimity of opinion today, 9 years later, about to what extent this pattern has to do with artifacts of recording, paleomagnetic recording, and to what extent it's real. There's still sharp dividing lines amongst some of us in the paleomagnetic community. However, also a 19100, that is 2000, paper in 2000, published by Jeff Love, which he gathered together all the VGPs, did a rational normalizing job as first done by Jean-Pierre Vallée and Xavier Quiddeleur, as I recall, for reversal records. He shows a histogram here in which there is certainly a what looks like a detectable statistical preference of VGPs, although not real strong, for the Americas and Asia. And bootstrap calculations suggest that this is significant at 95% confidence. So that's the real data. Well, we had two reversals in the tomographic simulation, and especially in this first one, you can see the VGPs, intermediate VGPs, clustering over the Americas. And this one here came out a little too dark in my slide, but there is somewhat preference for the Americas and also for a broad region out here. You can see it better in the histograms. So here's the first reversal. So this is what you can do with simulations. You can take stations all over the Earth and compute the VGPs, compute VGP densities, or look at their longitudes. And so we see a peak corresponding to this one here. Here we see a double or really a triple peak. So I would call this the Afro-Asia high. Now we have to remember this is this is for the tomographic model of imposed heat fluxes, which the heat flux coming out of the core does not necessarily look like this. This is a low order, now old, Su and Zwanski, 1994, deep mantle tomographically determined S-wave velocities. But then with the assumption that where the velocities are high, the material is cool, and cool material next to the core will let more heat out. So we see more heat coming out here and here where the velocities are low in this imposed CMB heat flux. But so the real question is, well, having imposed this, do we see some effect not only on the transitional VGPs where we only had two reversals, which is not a very large statistical sample, but for the whole time average simulation of more than 300,000 years with the unstable, the excursions and the reversal poles removed. And indeed, looking at the non-axial dipole field vertical component, actually the absolute value of the vertical component, because it changes signs with reversals, you can see that there's very strong, well, actually we've chosen our colors so you can see it. There's a visible concentration here and here. So yes, the simulations do pick up a geographical effect related to the imposed CMB heat flux. So this gives me more confidence in the VGP patterns that we see in the real data for the Earth, because I know it can happen now in this simulation. Now I'd like to change. Bill, I can't see my watch. What are we doing? 42. Okay. Now I'd like to turn to models C and E. Model C, if you look at the VGP latitude as seen at just one location on the globe, you see lots of reversals and what I'm going to call an excursion and a cryptochron here as a function of time. And this is the imposed CMB heat flux, to remind you. And looking here at the energy, now not plotted on a log scale, you can see large ups and downs in the blue axial dipole energy, the lows associated with each of these. And you can see in most of the cases, except the very first one, you can see that the non-axial dipole field is doing its part in trying to trigger a reversal or help a reversal happen. Big increases in the reds at these places here, even at this excursion here. But at the first one, we don't see anything like that. So there's lots of ways that reversals can happen, even just in these simulations, probably more in the Earth. Case C is interesting in that if we compute the VGP dispersion for case C, excluding the reversal and excursion times, we get a variation, a latitudinal variation that looks very much like the Earth. This computed for specialists among you by the method of Van Dam et al. And it'll be important to note later that the SV for case E is much, much lower. Well, during that excursion, what do the VGP show? What I call the excursion. Well, the true dipole indeed doesn't reach reverse polarities, and depending the sampling of localities on the globe of the VGP arising from the total field, you can see that we get a great variety, including a few places on the globe where the VGP does reach what we would call reversed polarities, even though the true dipole didn't. And this is probably, this is my model for the Mono Lake excursion. I think this is what happened in the Mono Lake excursion. What we were calling the cryptochron, you can see the true dipole does actually reverse. And at most localities, the VGPs do too, although around this region, the VGPs do not reach full reverse polarity. So this is perhaps instructive. For instance, here's a record of the Blake event from a study by the Vandervoot group. This is recorded in Chinese Lus in central China. And you can see actually a double swing of the field direction recorded here in this interval. But the important thing I want you to see here is that their VGPs, both normal and reversed ones, came out fully normal and reversed, as though it's easiest here for me to believe that indeed for the Blake event, the true dipole did reverse. And those places on the Earth where we don't see a full reversal, it's the effect of a non-dipole field, or in some cases maybe also sedimentary averaging. Well, we are very lucky in the cryptochron recording that one of the automatic infrequent data dumps of the simulation, time step 946, actually occurred. You can't afford to have these very often because they've got everything in them, and they take up too much memory. But the interesting thing here is that you can see that in the middle of that excursion where the field had gone to completely reversed, the poloidal field, the poloidal reversed polarity field shown by the dashed lines, it did succeed in reversing, but deep in the liquid outer core, here and here, and with also a field line going through the inner core, solid lines still had normal magnetic polarity. So it looks like in this case a good rationale for why the field swung back, changed polarity back to its original polarity so quickly, was that from the standpoint of the Earth, the reversal had not completely occurred, as was suggested a long time ago by Hollerbach and has been amplified by Gubbins and Zhang. But an interesting thing to keep in mind is that a lot of these opposite polarity field lines are not in the solid inner core. They're kind of associated with the tangent cylinder here, deep in the core, in the liquid part. Okay, to move into the last phase of the talk, here's the case ECMB heat flux. Here's the axial dipole energy and the non-axial dipole energy, and you see that despite large swings in this energy, there's quite a distance between it and the non-axial dipole field. And in fact, no reversals happened, and the VGP latitude is greatly constrained. Only once did it get down as low as 60 degrees. And this model ran for actually 350,000 years. And so this fits the idea of the probabilistic model of Alan Cox that I mentioned in the beginning. It also fits some exciting results that we heard just an hour ago or so by John Tarduno and his group, in which on single crystal paleointensity estimates from lava flows in the Cretaceous long normal, where there are no reversals happened for at least 30, maybe 35,000 years, that the paleointensity seemed unusually high, was unusually high, and the scatter in the paleointensity values was quite low. So perhaps that's the way things are going to turn out. Merrill and McFadden suggested also some time ago that a good thing to look at in terms of trying to understand the variation in polarity lengths going back in the past all the way to the Cretaceous normal superchron, where the reversal frequency was essentially 0, and before, that correlates with the VGP dispersion at the equator. So here you see McFadden and updated 96 estimate of VGP dispersion for these time ranges going back in the past. And you see that it was lowest, appears to have been lowest, during the Cretaceous long normal. And I took the VGP dispersion at the equator, this particularly nice one to look at, because it turns out that only the symmetric terms of the Gauss coefficients contribute to the VGP dispersion at the equator. So the axial dipole, all the ones for which n plus m adds up to an even number. Okay. Well, indeed, the VGP dispersion at the equator at 0 latitude for case E is way, way below that for case C, even with the same heat flux. So is this what's happening to cause a superchron? As well, Marilyn McFadden pointed out that, really following up on an early idea by Paul Roberts, that maybe the symmetry of the field in all of the Gauss coefficients may play an important role in the frequency of reversals. This diagram here shows the energy versus the degree 10112021 energy terms for these four cases. And you see here case E with the highest dipole intensity, and then an amazingly strong dominance of the odd terms over the even symmetric terms for this most stable of the dynamo simulations. And if you average over, instead of just going to 5,5, going up to n equals m equals 21 for these Gauss coefficients now at the core mantle boundary, by the way, you can see that the four models scale rather well in terms of their odd-even ratio and stability. That is, case E, the average odd is 19 times greater than the average energy, even energy. Case C is quite low. And this is during stable times. During the unstable times, well, E didn't have any, but you can see that the ratio drops significantly lower than what it was during stable times. So indeed, that seems to be a factor. Well, to finish, what is all this? What could it mean for the Earth? Well, we don't know for sure yet. There's been plenty of speculation already. Some of the speculation involves the idea of plumes. The nice thing about plumes is that, assuming they come from deep, they're produced at places where the mantle is hot, and therefore the CMB heat flux is low. And since they have a manifestation at the surface of the Earth as a plume head, as great large igneous provinces, as shown in this map, then by doing paleomagnetism and finding the paleolatitude of these, we can see whether there's any correspondence to the case E example. And in fact, the results that are available at present for two of the largest large igneous provinces, Ontong Java and Kerguelen, are at mid-southern latitudes, as happens to be the case for case E. And this is the very end. You noticed perhaps on this slide that I showed before that I had hiding away here the odd-even ratio for case S2, which is the small inner core case run by Glatzmeyer and Roberts. In this case, the inner core was 1/4 the size of today's inner core. And a great surprise, it's not at all what was expected for this simulation. One would have thought it would be unstable. Instead, it's super stable. And here's an example, and super symmetrical. Here's the angular standard deviation map of the VGPs. Very symmetrical, very low values at the equator, about one degree, and the odd-even ratio of 10,600. So the question that I would put to you here is, could this mean that as long as we had reversals of the magnetic field in the past, which would seem to be at least back 2.5 or 2.7 billion years, that we didn't have a really small inner core? Because I wouldn't expect this model to reverse ever if what I've been telling you up to now has any merit. So, thank you very much.